acids and bases. So by the end of this video, you will be able to describe the properties of acids and bases and relate them to their position on the pH scale. So, acids, let's look at some of their properties. Acids are chemical compounds that donate a proton, H+, to form a hydronium ion, H3O+. Now notice a proton is just a hydrogen atom which lost its electron, leaving behind only the proton. So that's why it has a positive charge of 1, H+. And this is what that looks like, because this definition is kind of hard to grasp if you've never seen it before, don't really know what it means. Say we have acetic acid, okay, vinegar. That is the structural formula, C2H4O2, and we put that in an aqueous solution. So you put it in water. That acetic acid is going to lose this proton. It's going to lose this proton. It's going to lose that, and it's going to give it to the water, creating hydronium ion. So a hydronium ion, that is H3O with a positive charge, H3O+. So look what happened there. We had the proton on here, and it's going to give it away to create a hydronium ion. So that is what an acid does. It donates a proton to form a hydronium ion. That's what that looks like. And since it gave away a positively charged proton, it's going to have an overall negative charge. This has an overall positive charge. And the result is that acids are strong conductors of electricity, because these ions, since they're charged, they can easily conduct an electric current. Acids react with many metals. For example, this copper penny is dissolving in nitric acid. Now the penny is brown. The acid is orange-ish, and when this penny dissolves, you see that blue. That blue is the copper ions inside of the solution. Acids taste sour. That's another property of acids. So the citric acid in lemons is what gives them their sour taste. Now let's look at bases. Bases, they're chemical compounds that accept a proton, H+, to form hydroxide ion. So while acids donated a proton, bases accept a proton. So they're like the opposite. And this is what that looks like. Say we have sodium bicarbonate, baking soda. This is what that's roughly what its structure looks like. Now, this is water, so if we put baking soda in an aqueous solution, so we're going to pour some baking soda in a cup of water, make an aqueous solution of baking soda, and what's going to happen is the baking soda is going to gain a hydrogen. It's going to gain a proton. But where is it going to get it from? It's going to get it from the water molecule. So watch what happens here. This gains, it takes it away from here, from the water, and what you have left is OH minus. And that's what bases do. Bases are chemical compounds that are going to accept a proton, taking it away from water, taking it away to form a hydroxide ion, OH minus. Now bases are slippery to the touch, and they attack oil and grease. And because bases do that, that's why bases are often used in soaps and in detergents. And that's why soaps and detergents are so slippery, because they're generally made of basic chemical compounds. Now, acidic solutions have high concentrations of hydronium ions, high concentrations of H3O+. This is a model of an acidic solution. You have a lot of H3O+ ions, but you only have a little bit of hydroxide ions, OH-. Why is that? Because acids are, remember, they're donating protons to form hydronium ions. So if I have a bunch of these molecules giving away their protons to make a bunch of these, then I'm going to have something that looks like that. Now, basic solutions, they have a high concentration of hydroxide ions, OH-. So over here, I have a low concentration of hydronium, little bit of H3O+, but I have a lot of OH-. And why is that? Well, because if I have a whole bunch of baking soda molecules in water, it's going to steal all of the protons, leaving hydroxide ions in its wake. And that's why it looks like that. Now, the pH scale. pH basically means power of hydrogen, and it is a measure of the concentration of H3O+, aka hydronium, in an aqueous solution. So we're going to measure the H3O+ ions in a solution. So this is my pH scale. It's on a scale of 0 to 14. And something is acidic has a pH less than 7. Alright, so any pH less than 7 is going to be acidic. It's going to have a high concentration of hydronium ions, but it's only going to have a low concentration of hydroxide ions. So we have battery acid with a pH of 0. It's extremely acidic, which means it has a lot of H3O+ ions in solution. Stomach acid is very acidic, pH of 1. Vinegar, pH of 2. And here's a couple more substances with their respective pHs. Acid rain has a pH of 5-ish, or around 6. Now, on the other end of the spectrum, we have our basic solutions. They have a pH greater than 7. They have a low concentration of H3O+ ions, but they have a high concentration of hydroxide ions, a high concentration of OH-. So we have our baking soda with a pH of 8. We have our toothpaste, pH of 9. We have our Windex with ammonia, a pH of 10. Soapy water, pH of 11. Clorox bleach, pH of 12-ish, 13-ish. And our Drano, which is the strongest basic substance, sodium hydroxide, pH of 14. Okay, so now, what about the middle? Right in the middle is neutral. You have an H3O+ concentration that is equal to the OH- concentration. Then you have a solution with a pH of 7. And a solution with a pH of 7 is not a solution, actually. It's pure water. Pure water has a pH of 7. It has the same hydronium, H3. It's the same H3O+ as OH-. So wait, before I move on, let me zoom out so you can get a full picture of the pH scale. Remember, lower pH means it's more acidic. Higher pH means it's more basic. And it all has to do with the concentration of H3O+. High concentration of H3O+, we're going to be acidic. Low concentration of H3O+, but high OH-, we're going to be basic. Now let's look at acid-base indicators. Indicators, they turn different colors in solutions of different pH. For example, litmus paper. Red litmus paper turns blue when you put it in a basic solution. And so that's right here. This red litmus paper has been put in a basic solution, turned blue. Blue litmus paper turns red when placed in an acidic solution. Another indicator is thymol blue. It turns yellow in solutions with a pH between 3 and 8. But it turns blue in solutions with a pH greater than or equal to 10. So if you look at the picture over here, I wonder if I zoom in. Looking at this picture over here, thymol blue. pH of 4 is going to turn yellow, as it's between 3 and 8. The pH of 10 is going to turn blue. Next, phenolphthalein. Phenolphthalein is clear in acidic solutions, but it's going to be pink in basic solutions. So you got to remember what the pH is for acidic and for basic. Phenolphthalein will be clear in any solution with a pH less than 7, but it'll be pink in any solution with a pH greater than 7.